Hi everyone, I'm Fleming and I'm a PhD student in the Chemie department at MIT. This poster is about a Julia package I've developed to enable practitioners to conveniently compute rigorous bounds on moments and related statistics of polynomial jump diffusion processes. So why should you care about this? Traditionally, the analysis of stochastic processes relies on brute force sampling, where we simulate a bunch of paths of a stochastic process and then use the statistics of this sample as proxy for the true statistics of the process. While this is generally a very powerful strategy, it may break down, however, if the process under investigation is highly volatile, stiff, or both, then rendering simulation expensive and convergence of sample statistics to the true statistics slow. In those cases, researchers often fall back on approximation techniques to recover tractability. But in the process of doing so, they introduce an unknown error, potentially leading to qualitatively wrong results. To address this issue, in this poster I'm looking at an alternative approach, so-called moment bounding schemes, which avoid sampling altogether and provide verified results that ship with hard error bounds. For that, I'm assuming that we are looking at a jump-diffusion process as shown here, where all relevant data such as drift coefficient, diffusion matrix, jumps, etc. are polynomials. For such systems, we cannot in general compute the moments directly due to the notorious moment closure problem. So we need a way to regularize that problem further. In moment bounding schemes, we take the following approach to that issue. We identify the minimum, or respectively maximum, value of some moment of interest, subject to a set of consistency conditions that, for example, reflect the dynamics of the underlying process or the support of its distribution. And since these consistency conditions are designed to be satisfied by the true moments of the process, this will generate valid lower and upper bounds on the true value of the moment of interest. It turns out that problems of this general form can be formulated as sum of squares programs and therefore be efficiently solved via convex optimization. Moreover, these problems actually lend themselves to be arranged in a hierarchy, which provides us with a mechanism to trade off more computation for better bounds, which is very handy in practice. So in principle, the Julia ecosystem has everything in store to implement moment bounding schemes. On the one hand, there are packages like Catalyst, Symbolics, and Dynamic Polynomials.jl to model stochastic processes for a wide range of applications. And on the other hand, there's everything to create and solve general sum of squares programs enabled by Jump and the MathOpt interface. However, it is still very difficult, in particular for scientists and practitioners that are not too familiar with optimization, to translate these high-level models to the bounding problems that we would like to solve in moment bounding schemes. And this is why I created MarkovBounds.jl, which is intended to close this gap by transforming this high-level problem data into bounding problems and solve them using the existing optimization infrastructure in Julia. If you are now intrigued and want to learn more about the theory of moment bounding schemes or how MarkovBounds.jl can help you study stochastic processes by computing bounds on stationary moments, moment trajectories, or even whole distributions, or go as far as to study stochastic optimal control problems and do many other cool things, please catch me at the poster session, send me an email, or check out the MarkovBounds.jl package.